And I'll go ahead and let me present for the document camera for us to look at weak acids. So in the last hour, we were looking at strong acids and strong bases, and we did a little review of what, strong versus weak acids meant. So let's see if I can find the paper that we went over. Right, so here it is. All right, so we looked at this for weak acids. We looked at how it exists at equilibrium. And if we look at it at the particle level, right, it's mostly molecules with very few ions existing, which is why it's at equilibrium. So what I want to look at first is the Ka expression. So just in general, we'll look at the Ka expression, writing it, and kind of what it means for it to be weak. And then we'll compare it to the Ka values down here, because I want to be able to compare Ka and talk about the strengths of weak acids. So if we look at writing the Ka expression, so the Ka expression, the A means that we were looking at an acid here. So we have an acid because it's producing H+. So we have products over reactants, H+ times A- over HA. There's our weak acid. So the more ions that we have, the higher our Ka value. Right? The more ions, the higher the Ka. And so the more ions we have, the higher the Ka, the stronger the acid. Now, you can have a strong weak acid, right? So if we have, for example, these 4 acids right here. Here is the Ka of chlorous acid, HClO2. Well, the Ka is 1 times 10 to the negative second versus 1.8 times 10 to the negative fourth. -2 is greater than -4. So chlorous acid would actually be the strongest of all of these weak acids, because the higher the Ka, the more ions, which means the more it dissociates, right? Or the more it ionizes. So also the higher the Ka, the more ionization. That means a higher percent ionization. Now, something else that I want to look at with writing the Ka expression, right? So we wrote the Ka expression of this. We just didn't include water because it's a liquid. But I want to go back and look at what a Kb expression would look like as well. So a Kb expression is written just like a Ka expression. So if you have this document, and for those that, if you are not in the last session, the review document, let me get it for you guys. The review document that we're going through right now, I'll put it in the chat for you. Copy link. So there's the review document. This is what we're going through right now. So this is actually back onto page 3 when we were looking at the strong versus weak acid, but this shows equilibrium, right? Equilibrium expressions, which means these are weak. The difference between Ka and Kb is that this B means we're looking at a base, which means we're producing hydroxide. So to write the Kb expression, it's still products over reactants, Hb times OH- over the concentration of B. Again, water is not included because it's a liquid. So Kb, lowercase b, means you should see hydroxide somewhere in the expression. Ka means you should see H+ in the expression. That's the only difference. Ka is for an acid, Kb is for a base. So again, if we take a look at this chart, so this table in this practice sheet We have chlorous acid up here at the top with a Ka of 1.1 times 10 to the negative second, all the way down to phenol, which has a Ka of 1.3 times 10 to the negative 10. So down here, 1.3 times 10 to the negative 10, that's actually the smallest value on this entire table. Because yes, these are both times 10 to the negative 10, but 1 is less than 5. So phenol has the lowest Ka. So that means out of this table, it's the weakest acid. Right? Because the lowest Ka means, I should say the least number of ions. So it's the weakest acid. Up here at the top, chlorous acid with a Ka of 1.1 times 10 to the negative 2. This is the highest Ka, which means it's the strongest acid out of all of these. Notice how they gave us the pKa? Right. Remember that if they give you the pKa, they give you the Ka. Right. The relationship between the two is that pKa is negative log of Ka. So if you have to go backwards, the Ka is 10 to the negative pKa. You need to know, right, how to take the pKa and figure out what the Ka is. So chlorous acid is the strongest acid. Phenol down here at the bottom has the lowest Ka, so it's the weakest acid. Now, in the last session, we were talking about the strength of the acid versus the base. So since this has the lowest Ka and it's the weakest acid, that means it's actually going to have the strongest conjugate base out of all of these. So since phenol has the lowest Ka out of this entire list, it's the weakest acid, that means that its conjugate base, right? So the phenolate ion here would be the strongest out of all of these. Or if we go up here to back to the top, right? Sorry, we keep kind of going up and down. This is the strongest acid, right? Chlorous acid is the strongest acid, which means that it would have the weakest conjugate base. So that means that the chlorite ion here is actually the weakest conjugate base out of all of these conjugate bases listed. Because remember, the stronger the acid, the weaker the base. So make sure that you can, think about strength of acids and bases like that as well. You'll see a couple multiple choice questions like that. So what I want to look at before we get into some calculations is I want to actually look at writing an equilibrium expression for a weak base. Because there was a question like this on the quiz, and I think this was a question that tripped a lot of people up. So this question, again, any that are on the lined paper are not part of that review document because I was using some sample quiz and test questions to write these. So this is, right, the equilibrium equation and expression for the hydrolysis, which means reaction with water, of CO3 2-. So this wants two things. It wants the equation and it wants the expression. So the expression is going to be one of the K expressions. Equation means it wants us to show the reaction with water. So let's start by writing the reaction, right? CO3 2- plus H2O. Well, I know that CO3 2- is aqueous because ions are always aqueous. Water's a liquid. It tells us it's at equilibrium, so I know there's a double arrow. All right, so now we have to figure out what is acting as the acid and what is acting as the base. Because we know it's at equilibrium, so we know it's going to be an acid-base reaction. Right? Hydrolysis is a type of acid-base reaction. So we have CO3 2- and we have H2O. Well, if it's an acid-base reaction, that means that a proton needs to be donated. CO3 2- doesn't have a proton to donate. There's no H in CO3 2-. So that means that H2O must donate the proton. H2O must donate the proton. So when HCO3 2- accepts just one H+, remember only one proton is donated at a time. When HCO3 2- accepts one H+, so we add an H, so we'll have HCO3, and we add a +1. So it's going to become HCO3-. Again, it's still an ion, so it's aqueous. Once water donates a proton, it's going to become OH-. Now, we're looking at this, and it now says write the expression. So here's the equation. CO3 2- plus H2O is at equilibrium with HCO3- plus OH-. Now it wants us to write a K expression. Okay, that's fine. Like, we can write the K expression. K equals, right? I'm writing capital A or capital K for now. We don't know what the subscript is yet. We don't know if it's an A or a B. It's products over reactants. HCO3- times OH- over the concentration of CO3 2-. Notice I did not include water in here because it's a liquid. Now, to figure out whether it's Ka or Kb, you look at what you have in the expression. I have OH- in the expression. OH- means we're dealing with a base. So this is the Kb expression. So CO3 2- was acting as a base here. Right. CO3 2- was acting as a base because it was accepting the proton from water. So we're looking at the Kb expression for CO3 2-. Right, so that was it for this practice question. But sometimes you have to predict the products on your own. So you have to figure out what can be the acid and what can be the base. In this case, CO3 2- could only be the base because it didn't have an H+ to donate. So that's just kind of a sample question with looking at Kb expressions. Okay, we have a couple other practice questions that we will get to eventually. So if you have this review document, we're going to be on the page that talks about weak acids, right? So page 10. So we looked at strong acids and strong bases. And now we're going to focus on weak acids and weak bases. So unlike strong acids, which we can just use the concentration of the acid to figure out the concentration of H+, we can't do that now. And we can't do that now because it only partially dissociates. So it's at equilibrium. All right, so this is just kind of a general example. If we have a 0.1 molar solution of some weak acid, HA, it has a value of Ka, we can determine how much H+ is formed by using equilibrium. So remember, when you have anything at equilibrium, you want to use an ice table, no matter what. Notice there's only 3 spaces here for HA, H3O+, and A-, because H2O is a liquid, so that does not get included. So we're going to be using an ice table for all of these calculations. So we're just going to jump right in. We're going to work through some sample problems because I want to be able to work through these, answer questions. Some of them, like, we're probably only going to do, number 1 or one of the sample problems, and then we'll look at weak bases and we'll talk about some other problems that we've done that we might not get to in this. So for this first sample problem, calculate the pH. All right, calculate the pH. So my goal is to find the pH of this weak acid. So the first thing you need to do is write the reaction. So like I had said before, a lot of times you'll see it written as a RICE table, R-I-C-E, for reaction initial change equilibrium. So always start by writing the reaction. So HC2, H3O2. Acids are always aqueous. I'm not going to show plus H2O. You could. I'm just going to do the simplified version. If you showed plus H2O, the only difference is instead of H plus here, it would be H3O plus and C2H3O2 minus. Notice how they gave you the Ka value. On test quizzes, right, you're given the Ka values. You saw that on the quiz last week. You were given the Ka value. So here we have our reaction. So I'm going to set up my ice table, I, C, and E. I'm going to go ahead and I was going to use a pencil. Where's my pencil? There it is. So I'm just going to use my pencil to fill this in. The concentration that they give you is always the initial concentration of the acid. 0.100 molar. We have 0 of anything else. The only thing it said is it was a 0.1 molar solution. All right, when they give us the Ka, that means that that's at equilibrium, right? That's the equilibrium constant. So they didn't give me anything else. Nothing else for this ice table. So I'm going to use x's. So minus x, and plus x. The reason I'm doing this is because to find pH, pH is negative log of the H plus concentration. So I need to figure out what is this H plus concentration at equilibrium, because I don't have any H plus initially. So we're going to find the pH once we reach equilibrium. So that's my goal of using the x's here. So 0.100 minus x, and x. The reason these are plus x is because it's starting at 0. Concentration can't be negative. It's only going to go up. So now we have this equilibrium row. Equilibrium can be used with the K. So the Ka expression is products over reactants. I know writing the K expression can be kind of annoying because you're just writing, products over reactants every time. But when it's free response, sometimes you are given points for writing the Ka expression. So just write the expression before you plug things in. So I'm going to have x times x over 0.100 minus x. Oh wait, I have a Ka value. I'm going to plug Ka in. Right, 1.8 times 10 to the negative fifth. There we go. So 1.8 times 10 to the negative fifth is x squared over 0.1 minus x. Right, you look at this initially and you're like, oh, the quadratic. Well, because K, I'm going to write this up here. Because Ka is less than 1 times 10 to the negative fourth, we can neglect x. So because Ka is less than 1 times 10 to the negative fourth, we can neglect x. If K were like 1 times 10 to the negative second, you'd have to use the quadratic. On the AP exam, which means on our exams, you will not need to use quadratic. You can assume x is small. So I'm going to write over here, assume x is small. When I assume x is small, I'm assuming that x is such a small number, it's not affecting that 0.1. So here's how I'm going to solve this. I'm going to do 1.8 e negative 5 times 0.1. And then to get x, I'm going to take the square root. So x is 0.00134. I did 0.134 because this initial concentration of acid over here, the leading 0 is not significant, but these last 3 are. So x is 0.00134. Now I want to just take a step back. I notice I underlined x here because that was H plus. I'm just going to do a quick label here. The H plus concentration equals x, which is 0.00134. The reason I labeled this, right, is because, again, on a free response question, you might get a point. they might award you a point for this H plus concentration. So make it easy to find. You don't have to box it because it's not your final answer, but maybe underline, label, something to make it easy to find. The importance of H plus is so that we can find the pH. Right? Negative log of 0.00134, which is H plus. I like labeling it like this because if I notice that it says pH equals negative log and I see an H plus, that tells me that this is actually pH. Negative log 0.00134. So the pH is 2.873. I did 3 decimal places because that represented 3 significant figures. If you just did 2.87, you're still okay. But I did 3 sig figs because of the 3, or I did 3 decimal places because of the 3 sig figs. So that's looking at calculating the pH, right? How to calculate the pH of a weak acid. This next sample problem is the same. So if you want more practice with pH and you want to work through this using this first one kind of as guidance, you can. I'm not going to work through this one right now. If you do work through this question and you want me to check your work, you can work through this. And if you want to send it to me via Remind, ask if you're on the right track. You can. I'll let you know, like, yeah, you're good, or you know, check this little part out. But this is calculating the pH. Another skill that you need to have is calculating Ka. Right, so another skill is calculating Ka. So let me look in the notes because we did these in the notes. So calculating Ka means that they would give you the pH. Example 13 in the notes. Yeah, example 13 in the notes. So let me make this note here. So example 13 in the notes. And that's also number 22 on mastering, right? MC for mastering chemistry. So example 13 in the notes, number 22 on mastering, has you calculating Ka, and they give you the pH. So it's a little bit different because you don't have X's here. Because if they give you pH, that tells you H plus at equilibrium. So another skill to make sure that you can do with weak acids is to calculate the Ka of a weak acid if they give you pH.
Mr. Ramaswamy.
Yeah.
I don't get the whole neglecting X thing. Can you explain that one more time, please?
Yeah. So in order to, so I'm going to rewrite this part down here, write it a little bit bigger. So 1.8, I'm sending it, so Ka, when I plug everything in to my Ka expression, it would look like this. And to solve for X, so if you look at this initially and you're like, okay, I need to solve for X. Well, I notice that I have an X squared and I have an X, right? Just a single value of X, not X squared. And so right now, if I were to solve for X, I would have to use the quadratic. Because if I multiply this over, it would be 1.8 times 10 to the negative 5th times 0.1 minus X equals X squared. So when you look at this, you're like, okay, I'd have to use the quadratic for this. Well, what we can actually do is, because all of our values are so small. So when I solve for X here, it was 0.00134. What we're doing when we're neglecting X, we're assuming that X is a very small number. So instead of having to use the quadratic formula here, we are just assuming that X is such a small number that when I do 0.1 minus whatever my value of X is, it's still essentially 0.1. So if I actually look at 0.1 minus 0.00134, right, it's actually 0.09866. So what it actually is doing is 0.09 Really, it's like 8.7 if I do 3 sig figs. I'm assuming that this X value is so small that I can round to 0.1 and still get a value of X that makes sense. So when we're dealing with KAs, so our equilibrium constant is less than 1 times 10 to the negative fourth, what that means is your Ka is such a small number that you have mostly just reactants. So I have mostly reactants. So if I have mostly reactants, I'm assuming that this minus X doesn't even affect my concentration of weak acid. So what we're doing is we're assuming X is small to prevent the use of the quadratic formula here. And we can do that because when we have such small values of Ka, that means that we have mostly just acid anyways, and there aren't very many ions. So we're assuming X is such a small number, it's not going to affect this initial concentration of acid, and then we don't have to use the quadratic formula in order to solve for a value of X.
Okay, thanks.
Yeah. And what we actually do is we just assume X is small every time that we use X's. So we're just assuming X is so small whenever we use X's so that we don't ever have to use the quadratic formula. Okay, so then we have, so at the top up here, right, it's another find the pH of a weak acid. So this is like the one at the bottom of page 10. If you need extra practice with finding the pH, you can work through that. But what I want to look at next is actually looking at the pH of a weak base. So the bottom half of page 11 is looking at a calculation of a weak base. So we can do this just like weak acids. It's just a little bit more work because we have an extra step that we have to take at the end. So in this sample problem, we're calculating the pH. So just like before, we're calculating the pH. But here they're telling me that it's a weak base. So there's a couple things that I'm going to take away from what it's telling me right here with a weak base. Is that tells me that I'm working with Kb because it's a base. But this is also telling me that the pH should be somewhere above 7 if it's a base. So when I'm getting my answer, I should have something above 7. If not, I need to go back and check my work. Now, just like we did with the weak acid, we need to start by writing the equation of the weak base. Now, when you look at this, you're like, wait, that doesn't look like a base. That has sodium in it. What I need you to remember, right, is that this is actually a salt. So this is actually a quick practice of salts. This is a salt because we have Na and C2H3O2. So from 7.4, we're talking about salts, and we have to split the salt in half. So if I split this salt in half, I have Na plus and C2H3O2 minus. So I want you to think about where each of these come from. Remember that your cation always comes from a base. Your anion always comes from C2H3O2, always comes from an acid. So I want you to think about each of these. Think about NaOH and HC2H3O2. So NaOH has hydroxide, so it's a base. Na plus is part of the lowercase b. This is a strong base. Well, remember, if you have a strong base, the cation that comes from that strong base is neutral. And then I have acetic acid, HC2H3O2. Well, that's not one of the 7 strong acids, so it's weak. So remember, if you have a weak acid, its conjugate base is also weak. So what I actually did with this salt is I split it in half. Na plus is neutral. It's a spectator ion. When we actually look at the reactions that take place in acids and bases, notice that it's always net ionic. It's always ions that we're dealing with. So Na plus is actually a spectator ion. I'm going to completely ignore it. It's neutral. It doesn't affect the pH at all. So really what this problem is having me look at is the acetate ion, C2H3O2 minus. It's having me focus on the acetate ion right? Tells me it's a weak base. So the acetate ion is a weak base. When we're dealing with bases, it's going to really help to show the plus H2O. So unlike acids that we can ignore the H2O, it's going to help to see the H2O for bases because we need to see where that H plus comes from. So because this is a weak base, it exists at equilibrium. Now we need to think about the reaction that takes place. So again, unlike acids where we can just split up the ions, the base, we actually have to think about the acid-base reaction that's occurring. So acetate is a base. It's going to accept a proton from H2O. It's going to become acetic acid, HC2H3O2. Water is donating 1 H+, so it's becoming OH-. So here is the reaction. The weak base plus water is at equilibrium with acetic acid plus OH-. Now this equation makes sense. If it's a base, right, it produces OH-. And that's what happens right here. So now we have our reaction. I'm going to set up an ice table. Right, so we have our weak base, told us this was a weak base. We have the reaction, produces OH-, which tells us it's a base. That's why we have a Kb value. So 1 times 10 to the negative third, that's the initial concentration of the C2H3O2-. I'm ignoring water because it's a liquid, and I had 0 of the products. All I had was the weak base, right, which came from the salt. Now we're calculating pH still. So what I'm used to looking at is pH is negative log of H+. That's what I'm used to looking at for pH. But just stop and think about it. Look at your equation. I'm trying to find the pH, and what I have over here is the acid, and I have OH-. Well, I might be able to use OH-, because if we have OH- from a base, we can figure out the pH eventually. So I'm going to try to figure out what this OH- concentration is at equilibrium. Didn't give me anything else for the ice table, so I'm going to go ahead and use x's. 1 times 10 to the negative third minus x plus x plus x. So here's our equilibrium information. Based on our equilibrium information and the Kb value, because we're dealing with a base, I can actually solve for x. So I want to point out the Kb value here. Kb is 5.55 times 10 to the negative 10. That's a tiny value of Kb. Right? This value of Kb tells me that I have mostly reactants at equilibrium. I actually have mostly weak base at equilibrium. Not very many ions at all. So I'm going to go ahead and use my Kb. I'll start by writing the expression HC2H3O2 times OH- over C2H3O2-. Again, water is not included because it's a liquid. And I'm going to plug everything in. So my value of Kb is 5.55 times 10 to the negative 10, x times x on the top. Right, I'm using what exists at equilibrium because this is an equilibrium expression. Over 1 times 10 to the negative third minus x. So again, when you look at this and you see that you have an x squared and an x, that initially looks like, oh no, I have to use the quadratic. But when we say assume x is small, remember, if you make the assumption, you have to write it down. We are assuming that x is so small, it's not going to affect this 1 times 10 to the negative third. So what I'm going to do is I'm going to solve for x. I'm going to solve for x right here. 5.55 e negative 10 times 1 e negative 3. Right? So that's when I multiply these two numbers together. And then to get x, I'm going to take the square root of that answer. So x is 7.45 times 10 to the negative 7th. I did 3 sig figs. We can round to less at the end. So going back to the question before on why we assume x is small. 1 times 10 to the negative 3rd minus 7.45 times 10 to the negative 7th. This is such a small number. Your equilibrium for this is still 1 times 10 to the negative 3rd. So that's why we can assume x is so small, right? It doesn't really make a difference. So now I want you to think about what x is, what x represents. Based on up here, x represents OH minus concentration. So I'm going to label this. Label that this is the OH minus concentration. Because if I take the negative log of this number, right, if I take the negative log of this number is OH minus. Think about what you're solving for. When you take the negative log of something, that's the lowercase p. So if I'm taking the negative log of OH, I'm solving for POH. So when I do negative log 7.45 e negative 7, again, that's POH. 6.13. That's POH. The problem wants pH. So pH is 14 minus POH. So 14 minus 6.13 is 7.87. Look at your answer. Look at this answer we just got, 7.87. Right up here, I wrote that the pH should be above 7. So a weak base calculation does take a little bit more work. Right? It takes a little bit more work because for a base, you have OH minus. And so when you have OH minus, then you have to figure out POH and then pH. There was, here it is. So if you want to look back at your notes, there's an example like this in your notes. It was example 18, which was also like mastering numbers 31 and 32. So those dealt with weak bases as well. So for weak bases, right, we have the reaction should produce OH minus. And so then it's the OH minus that we're using. And we have to find POH and then pH. So it's a little bit, right, little bit different because of what we're solving for. Any questions on the weak base?
So if it's like a salt or like ionic, like how NaC2H3O2 was,
Yes.
is the like the first part of it always just gonna be neutral?
If you're doing a calculation like this, more than likely, yes.
Okay.
If it's NaLi, those are usually the two most common examples, Na and Li. Yeah, it's just, you're just going to cross it out, especially because it says weak base. So weak bases are always the second part of a salt. So the first part,
Okay.
you always just ignore. Yeah.
All right, thanks.
Yep, you're welcome. All right, so what we're gonna do before, let me get them out. Before we look at percent ionization, I actually want to look at a couple practice multiple choice questions again. Actually, by a couple, we're just going to do the top one. Well, no, we can do both, actually. We'll do both. So, again, these are both practice multiple choice, which is why they're written on lined paper, because I took sample questions and changed some information. So, the first one says caffeine, which is C8H10N4O2, is a weak base with a Kb value of 4 times 10 to the negative fourth. The pH of a 0.01 molar solution of caffeine is, and I give ranges of pH. So this is really asking us, what is the pH of caffeine? Right? What is the pH of this molarity of caffeine? Now, a simplified way of writing a reaction, because a lot of people will look at this and they're like, how am I supposed to know what caffeine turns into? I'm going to treat caffeine, I'm just going to label it B for base. Okay, I'm just going to label it B for base. So I'm going to look at how this base interacts with water and what it produces. Because before I can do math, I need to make sure I have an equation so I can set up my ice table appropriately. Well, this B is the base, right? It's a weak base. It tells me that caffeine is a weak base. If caffeine is a base, think about what it will do in terms of a proton. If it's a weak base, it will accept a proton, which means water is the acid donating the proton. We don't care about the strengths. All we care about is that the base is accepting a proton. When it accepts a proton, you're adding an H+. It doesn't matter what B is, but you're adding an H+. You're adding an H, and you're adding a +1. So I'm just going to label HB+. Really what's happening is you're adding another H here, so it becomes C8H11N4O2+. We're just simplifying it here. Once water donates the proton, it's losing an H and a +1, so it becomes OH-. Ions are always aqueous. Now that we have our reaction, we can set up our ice table. So I'm going to plug in information. The concentration of caffeine is 0.01 molar. So the weak base here is 0.01 molar. I'm going to ignore H2O. It doesn't say anything about having the conjugate acid or OH- initially. It doesn't give us anything else. It doesn't give us anything else about equilibrium. Right? It's not giving us pH. It's not giving us any equilibrium amounts. So we're going to use X's. So the base is decreasing by X amount, and the conjugate acid and OH- are increasing by X amount. They're all increasing by the same amount because it's a 1-to-1-to-1 ratio. So 0.01 minus X, X, and X. Now, before we use the KB and we plug information in, I want to just take a look at the fact that this is a weak base. If it's a weak base, it's a base. If it's a base, where will the pH fall? If it's a base, think about where the pH will fall. Whether it's a strong or weak base, the pH should fall above 7. It might not be much above 7, but it's going to be above 7. I'm going to eliminate A and B. If you eliminate answer choices, you now have a 50-50 shot. So let's say that you're running out of time on multiple choice and you say, okay, I know it's a weak base. I know it should be above 7. I can eliminate A and B. You at least have a 50% chance of guessing it. So eliminate when you can. So now we have our equilibrium row. Remember that our equilibrium row is useful because we also have our KB expression. I wrote my ice table a little big, but that's okay. So our KB expression is products over reactants. And I know it's KB because we're producing hydroxide. And now we can plug everything in. So it says that the KB value is 4 times 10 to the negative fourth, and that's x squared over 0.01 minus x. So if, I'll write it up here, we assume x is small, we can ignore this minus x. And now we can solve for x. 4e negative 4 times 0.01. Take the square root. You can actually do this without a calculator, but you get a calculator for now. Right, so you could technically do this without a calculator. So x is 0.002. Think about what you need. If you're solving for pH, think about what you need. Well, I see that I have OH minus here. X is OH minus. So this value of x that I just found is OH minus. So if I take the negative log of 0.002, right, if I'm taking the negative log of OH minus, I'm finding the POH. So the POH is 2.70. I'll show you. Right, 2.69897, right, 2 sig figs, 2.70. So the pH is 14 minus 2.7. $11.3. So I've eliminated. Notice how you have 2 to 3 and 11 to 12. If people don't pay attention to what they're solving for here, they would circle A. You have to pay attention to what you're solving for. You see a question almost just like this on the multiple choice part of the test. Right? You have to pay attention to what you're solving for. Label what you're solving for. And so if the pH is 11.3, our answer is D. So notice that even though it's a weak base, the pH is still 11.3. So just because it's a weak base doesn't mean it's barely above 7. It could fall anywhere between 7 and 14. So that's looking at the weak base calculation. And the last multiple choice question that is listed here says, in which of the following solutions does the weak acid have the lowest percent ionization? So you do not need to calculate the percent ionization for each of these. Oh my gosh, that's going to take so much time. Right? You don't have to do that. Here's what I just want you to think about, right? Think about it conceptually. They're all the same molarities. When you have a multiple choice question like this, they're usually, especially for weak acids or weak bases, they're going to give you the same concentration. So they're all the same concentration. And I want you to think about the lowest percent ionization. So the lowest percent ionization, think about what percent ionization means. And we're going to talk about it in just a second. But you're looking at how many ions, right? How many ions at equilibrium versus the initial acid. So how many ions do you have at equilibrium versus the initial amount of acid? That's percent ionization. So the lowest percent ionization are the least number of ions at equilibrium. So the lowest percent ionization means the least number of ions at equilibrium. So think about what that means. The least number of ions at equilibrium means we're looking for the weakest acid. So in this, we're looking for the weakest acid. Well, this is why they give you the Ka values. You can look at the strengths of weak acids based on the Ka values. So the lowest percent ionization is the weakest acid. The weakest acid has the smallest Ka. Because the smallest Ka means the least number of products compared to reactants. So the smaller the Ka, the weaker the acid. So when you're looking at this, the weakest acid, the smallest Ka is times 10 to the negative 10. So our answer is actually A. So this is thinking about percent ionization conceptually, and thinking about what that means about the strength of the acid and how we can find the strength of the acid based on Ka. So the smaller the Ka, the weaker the acid, and the fewer the ions that exist at equilibrium. So that's looking at these two questions. The caffeine question was a math question. This percent ionization question is just a conceptual question, thinking about the strength of the acid based on percent ionization. So then the last thing that I want to look at is percent ionization. So percent ionization, we're going to focus on the percent ionization of an acid. So we just talked about what percent ionization is, but essentially we're looking at how many ions do we have at equilibrium versus how much acid did we start with. This equation is not on the equation sheet, but you need to know percent ionization. Please make sure you know percent ionization. So percent ionization is the H plus concentration at equilibrium divided by the initial concentration of the acid times 100. So in this, right, they tell you, this is kind of just giving you information. So a 0.2 molar solution of HNO2, that's a weak acid, has 9.6 times 10 to the negative third molar of H3O plus. What's the percent ionization? I do want to just pay attention really quick to the fact that this is a weak acid. If this were a strong acid, I'm just going to kind of make a note over here. If this were HNO3, which is a strong acid, it would have 100% ionization. All right, strong acids have 100% ionization. Weak acids do not. So percent ionization is going to be H plus at equilibrium over HA initial times 100. So here they actually gave us the information. It said that there were 9.6 times 10 to the negative third molar H plus in a 0.2 molar solution of weak acid. So we do H plus divided by the initial concentration of the acid. 3 divided by 0.2. And don't forget to multiply by 100. 4.8%. That makes sense. Weak acids should ionize less than 5%. Typically, the exception is HF. HF has a little bit higher percent ionization, around 13%. But most weak acids ionize less than 5%. So our answer here is 4.8%. Right, which means that 95.2% do not ionize. So again, if we think about what that means, if we had 100 HNO2 molecules in a beaker. So if is the key word here, I drew 100 HNO2 molecules in here. Only 5 of them would break apart. All right, so if we think about if we had 100 HNO2 molecules, we would have 5 H plus, 5 NO2 minus, and 95 HNO2s. So out of 100 molecules, only 5 of them break apart. Not very many at all. Then we have this sample problem down here, which it's almost 3 o'clock. So if you want to work through this question, right, just like the other one, if you want to work through this and you want to send me your answer to see if you're correct or not, you can. We did do a percent ionization question if you want to use your notes just as a guidance. We did percent ionization in example 16. So this will be like example 16 in the notes, which is also like 28 and 34 of mastering. So if you want to use that as guidance to help with percent ionization, you can. But then down here at the very bottom, just something important with percent ionization is that as we increase the concentration of an acid, so let's say I just have this weak acid, HA, A plus and A minus. As we increase the concentration of acid, so as we have more and more acid, the percent ionization actually decreases. And that's because of Le Chatelier's principle. So as we increase the concentration of acid, we actually decrease the percent ionization. So because of Le Chatelier's principle, as we increase the amount of acid, we have less, right? We see less ions dissociating. So as we increase the concentration, we decrease percent ionization. But most of the percent ionization questions are going to be math. So can you calculate the percent ionization like in this sample question? And then finally, again, just more practice questions if you want to work through them. Page 12 of this review document has more sample questions. So there's all 3 of these are multiple choice, but these first 2 go with this table, and then this bottom one is a separate multiple choice question on its own. So again, if you want to work through them, you want to make sure you have the right thing, you can send me those. What I'll probably do is just work through all of these, and I can send this out via Remind. So if you want to check answers, you can. I'll also, when I post the recordings, I'll add all of this into the description of the video on YouTube as well. And then what I do not have printed out, but I did add to the review document, is a review on the strengths of acids. So reviewing like how strong is, if you have acids like HClO, HClO2, HClO3, HClO4, so looking at the strengths of oxyacids, binary acids, things like that. So it is a little bit past 3, so I want to be able to get into kind of the office hours Google Meet.